CommaBody. What is CommaBody? It's a robotics dev kit that can run open-pilot, open-source software with over 1 million hours of usage in the field. Developed by comma.ai, it is made up of a 142 cm long pole and comma 3 head atop it. The pole is attached to a base with 2 wheels and no other limbs. Comma has multiple cameras, with sensors monitoring wheel speed and logged camera frames. It runs OpenPilot software and can be accessed through the Body Gym environment to control and log movement. Hi, I'm Diya Shakkottai. Over the summer of 2025, I was given the chance to work with a CommaBody robot at Texas A&M University in the James J. Cain building. My project was to work with research scientists in the lab in assessing and improving CommaBody's autonomous indoor navigation capabilities. Our CommaBody is trained using a VQGAN image tokenizer, NanoGPT model, and an MLP action head. VQGAN, Vector Quantized Generative Adversarial Network, taken from the CompVis Taming Transformers repository, is a model that converts images into discrete tokens for sequence modeling. The encoder compresses an input image into a smaller latent feature map, and each latent vector is matched to the nearest entry in a learnable codebook of vectors, producing a 2D grid of discrete tokens. The decoder then learns to reconstruct the original image from these tokens. The training process minimizes reconstruction, perceptual, and adversarial loss, using a discriminator to differentiate real and reconstructed images. The NanoGPT model stems from the Carpathy NanoGPT repository and is a decoder-only transformer model used for sequence modeling. It is fed the output image tokens from the VQGAN, as well as previous action and wheel speed tokens to generate hidden states that capture patterns in the sequence, which are used to predict future tokens and embeddings. The MLP, multi-layer perceptron, action head uses the token embeddings to predict actions for 16 time steps into the future, each having 9 logits representing angular directions. These actions are then fed to CommaBody to follow the generated trajectory. The MLP head can be trained separately or in parallel with the NanoGPT. We performed several training iterations for the VQGAN, GPT, and MLP models. We optimized them for better performance using different combinations of datasets and variation in the training parameters. A problem we had originally been facing was poor crash recovery and low endurance before spinning or coming to a complete stop. My first task was collecting data for the robot, which consisted of 3 sets. For 2 of the sets, CommaBody was manually controlled and followed a generally elliptical trajectory on white line tape, moving around open space in our lab. Comma was trained on a clear path for the first set and given obstacles in the second. In the third dataset, Comma was moved arbitrarily and explored more of the lab. Following data collection, we trained several VQGAN models on curated datasets to optimize for specific performance, for example, avoiding obstacles or navigating the entire lab. We were able to train 6 models, and the best performance came from the encoder trained on old labs data. We subsequently trained GPT models using the new VQGAN encoders to tokenize the collected data. Out of the 15 we trained, the most accurate trajectory predictions came from the July 24th checkpoint last GPT-2, moving in the desired elliptical trajectory and maintaining endurance, the split recent lapse GPT best val checkpoint, which performed similar to the former, and the Diya lapse random GPT-2 best val, which showed good trajectory mapping, obstacle avoidance, and strong recovery upon contact with other surfaces. These were all trained simultaneously with the MLP head. Given that the data was exclusively from the lab environment, we also monitored the ability of the robot to generalize its predictions to new out-of-lab settings. While its performance was less accurate outside of the training environment, it was still able to navigate well, despite never having seen images of those areas before. In summary, we were able to enhance Comma's autonomous indoor navigation through our improved pipeline. Going forward, our goal is to analyze Comma's performance and integrate new input factors to enhance trajectory predictions. This includes object annotation through use of a SAM2 labeling model, which would allow for improved obstacle avoidance. I'm so grateful to my mentors Dr. Alvika Gautam and Professor Srikanth Saripalli at Texas A&M University for guiding me throughout my internship and for giving me this opportunity. I look forward to working with CommaBody in the future.